Welcome. Today in this lecture we shall be doing a few problems on the natural gas recovery. In this what we shall be learning? We shall be learning about the estimation of the flow rate of propane in a propane refrigeration system, then the liquid fraction produced and the coefficient of performance for the propane refrigeration system, and how to estimate the ethane recovery to adjust the heating value. So, the first problem is like this, that we have a propane refrigeration system with a evaporator duty given as this value, which is operating between two temperatures, that is minus 40 degrees centigrade, which is at the evaporator, and 40 degrees centigrade at the condenser, and we have to determine the flow rate of the propane. So, here we again recapitulate what is the propane refrigeration system. In this is the compressor, condenser, receiver and the evaporator and jet through jetty valve. Now, here what we find that we have also denoted the various states, that is 1, 2, 3 and 4. So, these are 4 states through which the propane is undergoing the cycle, and along with that this is the pressure enthalpy diagram on which we are showing the change in the states starting from the 1 to 2, that is from the compressor. So, this is the compressor, then the condenser, then the JT effect, that the isenthalpy expansion, and then we have the ultimately we have the chiller. So, this is how these things are going on, and I am not going into details of this because these have been told to you in a separate lecture. We are just demarcating the particular data which have been given to us. So, here in the condenser the temperature is about 40 degrees centigrade, and in the chiller it is at minus 40 degree centigrade. So, these are the two temperatures given to us, and now what we are doing, that we shall be writing a steady state energy balance across the chiller to know the flow rate. So, at steady state we have the energy that is going in and energy that is going out, and energy is also coming in from the space which is to be refrigerated. Okay. So, from there we are getting this thing, and this is nothing but the evaporator duty. So, these are the energy effects, and here we are neglecting any other energy heat in-leak from the ambient into the system, or heat out-leak from the system to the ambient. So, under these assumptions, for a steady state energy balance, we know that energy that is going in plus the energy that is also coming in through the evaporator duty is equal to the energy of the vapor out. So, here we are writing this Q evaporator is equal to like this, that H1, there is a H1 here into m dot minus H4 into m dot. Okay. Now, this H1 and is H3 is what, that H4 is equal to H3, because we know this is an isenthalpic expansion. So, that is H3 is equal to H4. So, and H3 is the saturated liquid enthalpy at 40 degrees centigrade. From here we find that at this whatever enthalpy is there, this is the enthalpy at 40 degrees centigrade for the saturated liquid. So, the same enthalpy will be there also for this H4, and H1 is the saturated vapor enthalpy at minus 40 degrees centigrade. So, this is the enthalpy which is the enthalpy for the inlet gas stream, and we are converting this degree centigrade into degree Fahrenheit. Why? Because the thermodynamic charts which are available to us, they are given in the FPS system. So, this is the our study, the control arm for study, and here we have in from these properties of this saturated propane in engineering units. So, here we have this from this particular reference, we have taken this data, and for this 140 degree Fahrenheit we find these are the data for the saturated vapor. So, from here we find out the enthalpy, this that is for the vapor, that is about this 225 is the vapor enthalpy for 140 degree Fahrenheit. Sorry, this is the liquid enthalpy we are taking, this 113.690 as the liquid enthalpy from this table, and we are taking at minus 40 degree Fahrenheit, we are taking the vapor enthalpy to be 128.240. So, here we are reading these values and we are putting these values over here. Now, what we do after doing this, we are simply plugging in the values in this particular equation, and we are getting the flow rate as the evaporator duty divided by the difference between these two enthalpies, and after plugging the values we find this is the value of the flow rate. So, this is the flow rate of the propane through the system. Okay? And we see that how we are using the energy balance equation and the consideration that there is an isenthalpic expansion through the JT valve, we are able to solve for the mass flow rate of the propane. Now, we come to the same system. Now, here what we are doing, that we have to find out the liquid fraction produced and the COP of the refrigeration system, and here we have been given that we assume that compressor efficiency is about 77% and heat inlet into the system is neglected. So, again we write that the work done is, this we have derived earlier also. So, we find that work done is HB minus HA, that means this is the compressor. Okay. So, the work is done only at the compressor. So, we are writing that HB minus HA divided by eta IS, because actual work will be from A to B prime. So, this A to B, and this is the ideal work. So, this A to B prime has been taken as in terms of A to B and divided by this efficiency of the isentropic this compression, and this is the enthalpy of the vapor leaving the compressor is HB prime. HB prime here, this HB prime equal to HA plus this WC. Now, because we need all the values of the enthalpies, so we need to refer to the pressure enthalpy data for propane, and here we have the diagram for the pressure enthalpy of propane. Here we find that we have these, you can see that these are the constant temperature lines, these solid lines are the constant temperature lines, and here also you find the constant density line over here. Okay. And this particular curve is for the saturated liquid, and this particular curve is for the saturated vapor. So, with this what we do that for minus 40 degree Fahrenheit and 14.5 psia, we find out the, this is the one, this particular line is for this minus 40 degree Fahrenheit, and from here we can note down that wherever it is this intersecting this line, from this we find out the value of the we find this value, and here we have get the value of the HA as this value. We are reading from the enthalpy, we are reading from the x axis. So, this is the value of the HA, and then we have the HB value. This is again coming from the 120 degree Fahrenheit and 250 psia. So, here this is the line for the 120 degree Fahrenheit, and here we have the 250 psia will be somewhere over here. So, from somewhere here we are reading the value again of the H from the x axis, and this is the property table for the saturated propane, and from here we find the values of this 120 Fahrenheit and 240 psia. We find this is the value of the enthalpy and at HC and HD. And now we simply plug in the values to find out the work done per unit mass of the gas compressed, and we also find out the actual enthalpy of a vapor that is leaving the compressor from this particular formula. Okay. So, this is how we can solve for the work done, and then what we do, that we need to know the HD, and HD we know that this will be somewhere here, and to know this HD what we do, we take the help of the enthalpies of the saturated liquid and the saturated vapor, and for this we need the F, that is the amount of the fraction of the liquid present in the mixture. So, we write this particular formula to get the value of the enthalpy at this point, and we find that we take that HdV to be same as the HA. So, we are taking, because the H is taken to be the saturated vapor. So, HA is same as the HdV, and we are taking that HDL to be 0. and we get from this formula this particular value. This is, that is the about 46% of the gas is being liquefied, and COP of the gas is this from the formula we derived earlier in our lecture. So, we plug in the values and we get the COP to be about 1.1. Now, we come to another problem. In this problem, we are having this ethane recovery in the fractionator. So, here we are considering that we have already the chilled gas, and as we have studied earlier that the inlet feed gas is comes through a propane chiller and other chilled by the vapor residual gas. So, from that we are getting this particular chilled inlet gas, and that is going to a fractionator, and here we are this, it is on top we are getting the gas, and from the bottom we are getting the NGL. So, what we have been asked that if the residue gas sales gas must have a minimum higher heating value of this 1000 BTU per SCF. So, here this particular residual gas, this is the minimum amount of the heating value of the residual gas, and we assume that 0% recovery of nitrogen and methane and 100% recovery of propane in the recovered liquid stream. That means, 0% recovery means none of the methane and nitrogen is going out with the NGL. That means, all of them are going with the residual gas, and 100% recovery of propane means the whatever propane is there in the inlet gas, all of it is going into the NGL and none is going into the vapor stream upward. That means what? That except ethane, all the gases are either remaining in the liquid phase or in the vapor phase. Only ethane is going with both the vapor phase and the liquid phase. So, we have to determine the maximum ethane recovery obtainable from the inlet gas comprising nitrogen, methane, ethane and propane, and the gas concentration mole percent for each component in the residue. So, what we do that this is the inlet gas composition given to us, that is 3.5% nitrogen, 87% methane, 7% ethane and 2.5% propane. And we have to check that whether it is right or not. What we do, we just add them up and find it is coming to 100%. Now, what we do that we are assuming it to be ideal gas. After assuming ideal gas, we find, and we are taking a basis of 1 SCF, that is a standard cubic feet, and with this assumption, so we find that mole fraction is equal to volume fraction in case of ideal gas. So, if we multiply this volume fraction with this 1 SCF, we will get the partial volume of each of the components, and that is what we have found here. Now, what we do that these are the percent recovery as we given in the problem, that nothing is going in the liquid, so of nitrogen methane. So, we are finding that recovery of these two components are 0 and the whole of the propane is going to liquid. So, it is 100% recovery for the propane, and we do not know how much is the ethane recovery. And because we have to meet the heating value requirement at the top gas, so we also need to know the component heating values for the mixture, because these will constitute the contribute to the total heating value of the top gas. So, here we find that nitrogen is supposed to have no heating value and only the hydrocarbons are having the heating value. Now, the residual volume, that is the volume which is going with the gas, is obtained like this. We are summing up with the partial volume and 1 minus recovery, that is this is the fraction which is going with the top gas. So, we plug in the values of all these things and we get this particular residual gas volume in terms of the unknown for the recovery of the ethane. And now, we find the total enthalpy of the residual gas from this particular formula. Again, this is an average volume fraction based formula. So, we are doing that volume of the each of the gases into 1 minus Fi into HHV of each of the components, and this will be totally divided by the total amount, total volume of the gas will be the this whatever is the desired minimum HHV of the residual gas. So, when we plug in the values of all these particular variables, we find this is the fraction of the ethane that is going out in the system. That means 52% of the ethane is going with the liquid and rest 48% is going with the vapor. Now, the next part of the question was to find out the composition of the residual gas. So, in this case what we do that now we again recalculate the residual gas concentration from this particular formula, that Vi into 1 minus Fi. So, we are getting these values, and this is coming out to about total is about 0.9386, and now that is this is the total one. And to find out the composition, what we simply do, we just divide each of these values with this value, and then what we do, then we do this, we are getting these values, and we find that ultimately these will add up to 1, and in percentage what we do, that we just simply multiply each of these with 100, and we get in percentage term, that we find that in the residual gas, initially it was 3.5%, it has increased to 3.7%, methane was 87%, it has now gone up to 92.7%, the ethane was 7%, it has now gone down to 3.6%, because rest of it has gone with the liquid down, and this down 2.5%, there is nothing. That means no propane has gone with the residual gas from the top. So, this is how we are able to find out the composition of the residual gas, and these are the various references you may refer to for detail of these processes. Thank you.